I'm Ken Ribbett, AMS President, and it's my very happy duty to introduce this year's Colloquium lecturer, who's Benedict H. Gross from the University of California at San Diego. I don't want to take too much time to say things about Dick. He's a wonderful guy, a wonderful mathematician, and as you'll see, a fabulous communicator. I just want to say that he has been decorated with prizes throughout his long career. He has one of the first MacArthur fellowships given to a mathematician, the AMS Cole Prize that he won with Don Zagier and Dorian Goldfeld for settling affirmatively a conjecture of someone named Gauss. He is a member of 2 academies at least. He's had 34 graduate students according to the Math Genealogy Project, some of whom I've seen in the last 5 minutes. His list of collaborators is immense and spans many different subjects of mathematics. It doesn't quite run from A to Z, but it does run at least through Bhargava and Zagier. Dick has a wonderful knack for identifying fruitful problems and assembling the tools to tackle those problems, and just consistently gets wonderful results that really shows off the power of mathematics. So, Dick, please take over, and we look forward to your very first talk on complex multiplication, which, by the way, is the very same subject as that of your doctoral dissertation written over 40 years ago. Okay.
Thanks, Ken. It's an honor to follow you. I think you've been a great president of the AMS, and only a couple more weeks to go. I should say that I owe Ken my first job. We shared a thesis advisor, John Tate, and Ken was working as an instructor at Princeton when I was thinking of applying for a job. And so I went into John's office, and I was about to ask him where I should apply, et cetera. And he looked at me and said, "Oh, Dick, I'm so glad you're here. I've just heard that from Nick Katz that Ken Ribbett is leaving Princeton and going to Berkeley, and can you just take his job?" I said, do I have to apply for it or something? No, let me just call him back right now. He said, also his apartment is available. You'll take the apartment too? Anyhow, it's a pleasure to give these lectures. I hope I can make this subject comprehensible to you. It's a subject I've worked in and loved for some time. So what complex multiplication is, it's a part of number theory that it involves the interplay between 2 areas. One is the theory of imaginary quadratic fields and their rings of integers and subrings. And the other is the theory of elliptic curves. And they play against each other in very beautiful ways. It has a very long and one might say twisted history. It's been around over 200 odd years, but I'm not a historian. If you want to read some episodes of its history, which I consider written by an expert in mathematical history, I can recommend this paper by Norbert Schappeker. He calls it a comedy of errors, because when you really do look at mathematical history, it goes forward, it goes backwards, it goes any which way except the way that we present it. But I'm going to present it as if it were a linear progression and do it historically, in the sense that the first lecture I'm going to cover perhaps the first 200 years of the subject, and from 1751 to 1951. 1751 is an important date. It's really the beginning of the modern theory of elliptic curves. It's when Euler was asked to review Fagnano's work on the Lemnis gate, and he began his investigation of what we now call elliptic integrals, which became the theory of elliptic functions, which became the theory of elliptic curves. And 1951 is also an important date, because that's when Heegner published his solution to the class number 1 problem, which I'll discuss. And in the second lecture, I'll do the next 50 years, which I call the present, because that was a period where I was more or less conscious. And then the last lecture, I'll do the period from in the 21st century, where there have been a lot of exciting developments, many of them very discussed in a special session at this meeting. I'll try to highlight some of those for you. So I won't start with elliptic curves, where the subject really began, but I'll start with the neighboring subject, the imaginary quadratic fields. And that began with the work of Lagrange and Gauss on positive definite quadratic forms, binary quadratic forms. So those are quadratic forms in two variables with integer coefficients, a, b, and c. A and c are positive, and the discriminant, b squared minus 4ac, is negative. That means that the quadratic form only represents non-negative integers. And we'll assume in these lectures that the discriminant is as square-free as possible, given the fact that it has to be either 0 or 1 mod 4 because it's congruent to square mod 4. So the square-free discriminants, or the most as square-free as possible discriminants, are called fundamental discriminants, and there are an infinite number of them, and they start with -3 and -4 and -7, -8, etc. And for each of these negative discriminants, you can act on quadratic forms by changing the basis, mapping x and y to integer combinations of x and y that give a basis of the same rank 2 module. And that changes the coefficients of the form, but Lagrange knew that it didn't change the discriminant. So it acts on all the different possible binary forms of discriminant D. And what Lagrange first proved, not for SL2Z, but for GL2Z, and then Gauss did for SL2Z, is that the number of orbits on the forms of discriminant D is always finite. They developed a theory of reduction of quadratic forms to show that every orbit contained a form of a certain type, and then it was very easy to show that there were only finitely many forms of that type. And the number of these quadratic forms in an orbit, the number of orbits of SL2 on the binary quadratic forms, is called the class number of the discriminant and denoted H of D. And once you prove something is finite, you want to know how large it is. And Gauss made extensive investigations in the Disquisitiones about these class numbers. So here's a picture of Gauss. He appeared on the German 10-mark bill before they went to the euro. And if you look carefully, let's see if I can show it to you, they have a little normal curve there. Okay? So when they made the 10-mark bill, they went around and they tried to see something of Gauss that would be recognizable to everyone. And of course, they didn't choose his number theory. That would have been nice if they had put up the theorem of quadratic reciprocity or something. But they felt everybody must know about the normal distribution. And so they went through Gauss's papers, because the Germans were very systematic and they didn't want to put up just any normal distribution. They wanted to find a normal distribution in Gauss's papers. And I found this out from the librarian at the Göttingen Library. They looked through all of Gauss's papers and never found a graph of the normal distribution. They found many calculations of the integral from a to b of e to the minus x squared dx, but no actual graph. He didn't think about it that way, and so they just drew one. Anyhow, Gauss made the following two conjectures. One was that the class number grew essentially at the same rate as the square root of the discriminant. In particular, as the discriminant got larger and larger, so did the class number. And he conjectured also that the class number was one in only 9 fundamental discriminants, and these are the 9, -3 up to -163. And that problem was solved, as I'm going to show you at the end of the lecture. I'll show you how. But we still don't know, really, that the class number grows effectively at the same rate as the square root of the discriminant. We know it goes to infinity now with the discriminant, but not at the same rate as the square root. What he was able to prove was the theorem on average, that if you sum the class numbers for all discriminants of absolute value less than t, it was a constant times t to the 3/2. So if you sum something which is about x to the 1/2, you'd expect to get something the size x to the 3/2. So that gave evidence for it, and the proof of this was the beginning of the subject we now call the geometry of numbers. All right, now here's some surprising consequences of the fact that the class number when the discriminant is -163 is 1. The first is obvious, that all the forms of discriminant -163 lie in the same orbit, and they're in the orbit of this form, which happens to have discriminant -163. The second, which was discovered by Euler, is that if you take that form and you take the y away and you just evaluate it at x equal 0, 1, 2, 3, up to 39, then the resulting number is always a prime number. It looks like you have a prime number generator here. Euler was very impressed with that. It doesn't work after 39, but you get a lot of primes in this way. And the third is that if you take the exponential of pi times the square root of 163, you get a number which is almost an integer. And we'll see why that's true by the theory of modular functions. So this makes it extremely unlikely that there were any discriminants beyond this, which had class number 1, because you would have had some even better prime number generator, and even an exponential of a transcendental quantity that was even closer to an integer. All right. Now, the modern point of view on imaginary quadratic discriminants doesn't use binary forms. It uses ideals in quadratic rings. So if you let A be the ring generated by two elements, the integers 1 and d plus the square root of d over 2, that happens to be the ring of integers in the imaginary quadratic field where you join the square root of the discriminant, which is a subfield of the complex numbers. And a non-zero ideal of that ring, and if you pick a basis for it, which is oriented in a certain sense, it gives you a quadratic form by taking the norm of elements in the ideal and dividing by the index of the ideal in the ring of integers. And that's an integral quadratic form of discriminant d whose orbit depends only on the ideal class of the sub-ideal of the ring of integers. And so this gives a translation from the theory of orbits of SL2Z on binary quadratic forms to ideal classes in imaginary quadratic fields, a translation that was made in the mid of the 19th century by Dedekind, and that's the way people usually think of it. And so this number of binary quadratic forms turns out to be the order of the ideal class group, which I call pick of A, and in particular, the orbits form an abelian group. And Gauss had done this in an extremely complicated way, defining a composition of two binary quadratic forms where the composed form depended only, the orbit of the composed form depended only on the orbits of the original forms. Well, we would now say we just multiply ideals, and if you multiply principal ideals, you stay in principal ideals, so you get an ideal class group. And the class number is 1, that's the class number 1 problem, if and only if the ring of integers is a principal ideal domain, namely every ideal is generated by one element. Well, let's take the first case where it isn't. When d is minus 20, the ring of integers is generated by square root of 5. You don't have unique factorization. All the books show you this factorization. 2 times 3 is 1 plus square root of 5 times 1 minus the square root of 5. But neither factor is divisible by the factors on the other side. So the class number is not 1. It's not a principal ideal domain. And here there are two ideal classes. The class number is 2. One is the full ring of integers, and another is an ideal of index 2. And the two binary quadratic forms I've given over here. There are two orbits. And for larger values of the discriminant, it turns out that it's better to go back to the classical methods to compute the structure of this group by using the reduction theory of binary quadratic forms. I should say that Manjul Bhargava redid the theory of composition of quadratic forms in his PhD thesis, and that gives a very fast way of computing in the ideal classes. And I should say that there are many predictions about the structure of this class group that we are still working on today. For example, there are these heuristics of Henri Cohen and Hendrik Lenstra that predict that the odd part of this abelian group, leave away the two primary torsion, but the odd part of the group should be cyclic 97% of the time, more than 97% of the time. Nobody can prove that. Here's a picture of Henri and Hendrik at Oberwolfach. Well, that's a quick summary of the class groups of imaginary quadratic fields. What about elliptic curves? Well, over the complex numbers, which is where Euler began their study, every elliptic curve can be viewed as the complex numbers modulo a lattice. A lattice is a discrete co-compact subgroup of the complex numbers generated by two complex numbers which are independent over the reals. And the homomorphisms from one elliptic curve to another are just the maps from the complex numbers to themselves, the linear maps, z goes to alpha z, that take one lattice into the other. In the isomorphism classes, so you get an isomorphism if you can go backwards, are the lattices up to scaling. So the two curves would be isomorphic if lambda prime was equal to a multiple of lambda. Now, an oriented base lattice gives an invariant in the upper half plane. If you take the ratio of the two basis elements, that's not a real number, so it's a complex number with either positive or negative imaginary part. You say it's oriented if it has positive imaginary part. And that number in the upper half plane depends only on the base lattice up to scaling, because if you scale the lattice, you scale both omega 1 and omega 2, and you have the same value of tau. And if we change the basis of our lattice, omega 1 and omega 2 map to a different basis, by an element in SL2Z, you get a new invariant, and it's the SL2Z orbit of tau on the upper half plane that's really the analytic modulus of the elliptic curve. So the orbits of SL2Z on the upper half plane form an analytic space which gives the different isomorphism classes of complex elliptic curves. Well, let's make an elliptic curve from an imaginary quadratic field, because that's where the two subjects start to interact. If you have a non-zero ideal of the ring of integers in an imaginary quadratic field, that gives you a lattice in the complex numbers, because the imaginary quadratic field embeds in the ideals generated by two elements. They're not dependent over the real numbers. So if you take your lattice to just be the ideal, thought of as a subgroup of the complex numbers, you get an elliptic curve. And those lattices are very special because there are a lot of maps from the lattice to themselves. For example, since it's an ideal for the ring of integers, the ring of integers multiplies the lattice into itself, multiplies M into itself. And so it turns out that's the full ring of homomorphisms from E to E. And in that case, we say the elliptic curve has complex multiplication. For most elliptic curves, if you just write down an arbitrary lattice in the complex numbers and you ask which complex scalars take that lattice into itself, it's just multiplication by an integer. Any integer multiplies a subgroup into itself. But for these curves where the lattice comes from an imaginary quadratic field, you have extra maps from the curve to itself. Those are the complex multiplications. And a complex multiplication has a kernel, and namely a finite subgroup of E, and that's the points in alpha inverse of the lattice, modulo the lattice. And the size of that is the norm of the element alpha from the imaginary quadratic field. Okay. Too high. Okay. Slow down. Okay. So, as I say, I'm just trying to give an idea of the complex theory of elliptic curves. Each elliptic curve corresponds to a lattice, and there are special lattices that come from ideals in imaginary quadratic fields that give special elliptic curves, the ones that are called with complex multiplication. They're the ones that have maps from themselves to the elliptic curve, which are not just given by multiplication by an integer. Isogeny is just a map from the curve to itself. That's what I meant. I should have said that. And when you have a map, you can get a kernel, because something which is mapped into the lattice is something that maps to the 0 point of this elliptic curve. And those points are the points in alpha inverse times the lattice, modulo the lattice itself. And so remember that to an ideal in an imaginary quadratic field, we had a binary quadratic form, ax squared plus bxy plus cy squared. And the analytic modulus of the elliptic curve with this lattice, remember the analytic modulus was the ratio of the two generators of the lattice, is this point in the upper half plane which solves that quadratic equation. Namely, it's minus b plus the square root of the discriminant over 2a. And the isomorphism class of this elliptic curve, we saw, depends only on the lattice up to scaling, so it depends only on the ideal class of the ideal, not on the ideal itself, just on the ideal class. And particular, since there are only finitely many ideal classes, there are only finitely many isomorphism classes of elliptic curves which have complex multiplication by this ring A. That's the fundamental thing we're going to use. From the analytic point of view, the finiteness of the ideal class group means there are only finitely many curves that have complex multiplication by this ring of integers up to isomorphism. That's going to have some profound implications when we consider the other way of looking at elliptic curves. Because the theory of elliptic functions, as developed by Euler and later Eisenstein and Weierstrass and Kronecker, gives another way of looking at elliptic curves entirely. Instead of the complex numbers modulo the lattice, they show that using elliptic functions, namely functions on the complex numbers that are periodic with respect to the lattice, you can embed the elliptic curve in the projective plane. And the image satisfies a cubic equation. So elliptic curves have, in one sense, an existence as the complex numbers by lattices. That's an existence in complex analysis. And they also have an existence in algebraic geometry as cubic equations in the projective plane. And the coefficients of that cubic equation come from the lattice. And Weierstrass proved that the coefficient of z squared x, G2, is the sum over the non-zero elements in the lattice, 1 over lambda to the 4th power times 60. That's a convergent sum. And G3 is 140 times the sum over the elements, non-zero elements in the lattice, lambda to the minus 6th power. And they also proved that if you took this polynomial in G2 and G3, this polynomial in the coefficients, that discriminant was non-zero. That meant that the cubic equation that one got from a lattice turned out to be a non-singular cubic equation in the projective plane. So those are the two ways that an elliptic curve lives. One is a lattice, and that can be constructed from ideals of imaginary quadratic fields, and another as a cubic equation. Okay. If you scale the lattice, remember you get the same elliptic curve, the coefficients of the cubic equation scale because you're summing over the inverse 4th powers or the inverse 6th powers. So G2 scales by alpha to the minus 4th, G3 scales by alpha to the minus 6th, and delta scales by alpha to the minus 12th. And then the miracle is that if you take the ratio of G2 cubed over delta, and you call that J, that depends only on the lattice up to scaling, because both the numerator and denominator scale by alpha to the minus 12th when you scale the lattice. And consequently, this number that you get from the coefficients of the cubic equation is an invariant of the isomorphism class of the curve, just like the SL2Z orbit of tau was an analytic invariant of the elliptic curve. Okay. If you have any automorphism of your complex numbers and you conjugate the coefficients of the equation, then since J is a rational function of the coefficients, it conjugates in the same way. So if you call the curve E sigma, let's see if I can do this, the curve with these coefficients, then the J invariant of E sigma is the J invariant of E conjugated by sigma. Okay. Now, in the algebraic geometry part of the world, we saw a homomorphism from one elliptic curve to another in lattices was just multiplied by scaling the lattice. But in the algebraic geometry part of the world, a homomorphism is the embedding of the function fields, the fields of functions on F into the fields of functions on E. So it's given by rational functions, x prime and y prime, call them R and S, such that x prime and y prime satisfy the equation for the elliptic curve F, the cubic equation for F, whenever x, y satisfy the cubic equation for E. That embeds the function field of F into the function field of E. And in particular, if we conjugate the coefficients of these rational functions by any automorphism of the complex numbers, it gives a homomorphism from the conjugate curves to the other conjugate curve. Well, this says that if a curve has complex multiplication and we conjugate the coefficients of the homomorphism from E to E, we get a homomorphism from E sigma to E sigma. And in particular, E sigma, the conjugate curve, also has complex multiplication because it has these additional maps from it to itself. If E had additional maps, so does E sigma. Okay. Well, that says there are only finitely many isomorphism classes with complex multiplication because they correspond to the ideal classes of A. And so the conjugates of this J invariant lie in a finite set of cardinality, the class number. So if you take any automorphism of the complex numbers and you conjugate J by that automorphism, you land in this finite set of the J invariants of elliptic curves with complex multiplication. Well, if that's true, the J invariant has to be an algebraic number of degree less than or h of d. Namely, it has to satisfy a polynomial whose degree is less than or equal to the class number. And this is the remarkable fact about elliptic curves with complex multiplication. They start off as being defined as completely analytic objects. You take their J invariant, that's a priori just a complex number, but the existence of these extra endomorphisms forces the J invariant to be an algebraic number. That's the miracle. And in fact, Kronecker proved much more. He proved that it's not just an algebraic number, but it's an algebraic integer. There are no denominators in it. It satisfies a monic polynomial with integer coefficients of degree exactly d, not less than d, but exactly d. And then moreover, and this is just for the number theorists, the number field generated by the invariant over the imaginary quadratic field is what's called the Hilbert class field, the maximal unramified abelian extension. Well, that's one of the great theorems in the 19th century on complex multiplication. And to give you an idea how beautiful it is, here are some J invariants that one can calculate, and these have been tabulated now for the small class numbers. When you have class number 1, the J invariant has to be an integer because it's an algebraic integer of degree 1. Whoops, let's try that again. So when the class number's of 1, the J invariant turns out to be an integer. And here's this J invariant of minus 163, which is very close to e to the pi root 163. And when the class number is 2, the J invariant has to be an algebraic integer of degree 2, and here it is for the case of square root of minus 15, which has class number 2. The J invariant lies in the real quadratic field generated by square root of 5. And these have been tabulated for class numbers less than 10. Now, these J invariants with curves of complex multiplication are called, in the classical literature, singular moduli. And one of the things Zagier and I found, which was extremely surprising to us because we thought the theory was all closed by the beginning of the 20th century, was that there's a nice formula for the difference of two singular moduli of different discriminants. And in particular, the only primes that divide them are very small. They have to divide a positive integer of the form dd prime minus x squared over 4, so they have to be less than dd prime over 4. So for example, if you take the two largest cases of class number 1, minus 67 and minus 163, and you take the difference of their J invariants, you find a number which is enormous, but all of its prime factors are small. And you think things like this would have been noticed because there have been tables of these things lying around for 50 years, but no one had taken a look at the difference and factored them. So we give a formula not only for which primes divide it, but what exponents of the prime divide the difference. This is a picture of Don. At the time I worked with him, which was in the 80s. He defies age. He looks exactly the same today. And when you meet a person like Don Zagier, you quickly come to the conclusion that life is unfair. I met him when I was 25, and he had just turned 24. So we became friends at a young age. I was a second-year graduate student at Harvard, and he was a distinguished visiting professor. So that gives you this idea of the unfairness of life. He really is an example of a fantastic prodigy who continued to produce great mathematics his whole lifetime. He got out of high school when he was 13 and was determined to go to Oxford. So he took the A levels and O levels, even though he was educated in the United States, and applied to Oxford and was told that he couldn't go at 13 because they didn't take any undergraduates who were under 16. So he went to MIT. And he finished MIT in 2 years and then applied to Oxford as a graduate student. And they accepted him when he was 15 because there were no regulations about not taking a graduate student when he was 15. He finished his DPhil thesis when he was 19, went to Bonn to work with Friedrich Hirzebruch, and as I say, by the time I met him in my young 20s, he was already an international hero. All right. Now, we've talked about the J invariant. That gives the isomorphism class of elliptic curves over the complex numbers. And that says that all elliptic curves over the complex numbers can be parametrized by the points of the complex line, the J line. But if you give a little additional information on the elliptic curve, like a subgroup of its torsion subgroup, the points killed by multiplication by n, you get curves which are finite covers of the J line. And over the complex numbers, the n torsion on an elliptic curve is a group of order n squared because it's n inverse times the lattice modulo the lattice. So Kronecker and Weber studied a certain curve which covers the J line, which gave an elliptic curve together with a cyclic subgroup of its points of order n. And this turns out to be a quotient of the upper half plane, not by the full group SL2Z, but by a subgroup of finite index in SL2Z, which consists of the integral matrices where C is divisible by n. That subgroup stabilizes a cyclic subgroup. And this is a very interesting curve. And the projective curve, which you get by completing it, turns out to have function field generated by two very simple functions. The first is the function J, the isomorphism invariant of the elliptic curve, and the second is the function J evaluated not at the point tau, but at the point n tau. And those two functions satisfy a famous algebraic equation over the integers called the modular equation. Now, the map that takes an elliptic curve and a cyclic subgroup to the modulus of an elliptic curve is defined over the rational numbers. This modular equation is defined over the rational numbers. And Kronecker noted, and this was a key observation, that when you had a curve with complex multiplication, its torsion points had very, very special behavior. So for example, if the curve is defined over a field L, and it has complex multiplication, then the points of order n on the elliptic curve, which satisfy some equations, actually generate an abelian extension of the field L. And this was Kronecker's liebster Jungentraum, my lovely dream of youth, for constructing abelian extensions. He wanted to take elliptic curves with complex multiplication and adjoin their torsion points. And it led to another wonderful German expression of his Grenzformel, his limit formula, which related these abelian extensions and the units in these abelian extensions to the first derivatives of certain infinite series. And the infinite series were like the zeta function, but instead of n to the minus s, you took a binary quadratic form and evaluated it at the minus s, and you summed over all m and m, which were non-zero. So these are two of the great results of 19th century theory of complex multiplication. The first being the construction of abelian extensions, and the second relating the units in those abelian extensions and their logarithms to values of these L functions. Here's a picture of Kronecker. He looks a little like a banker, but he in fact was a very inventive mathematician of the second half of the 19th century. Now, I want to tell you how you can formulate some of Kronecker's results in a slightly more modern way. So we assume that the curve has complex multiplication, and the smallest field it can be defined over is this Hilbert class field, because that's the field generated by its J invariant. And the J invariant certainly is in the field of definition of the curve. If you assume more, that the primes which divide n being what's called the conductor of the curve, the primes which has bad reduction, are split in the ring of complex multiplication, then you can find cyclic subgroups which are defined over the same field. That's the remarkable thing. You don't have to go any further. And so you get points on the covering curve x0 of n, elliptic curves and cyclic subgroups, above the point J of E, which are defined over the same field as the point J of E. So generally when you have a covering of curves like this, and you have a rational point on this curve, if you look at the points in the fiber of the covering, the whole fiber is defined over the rational numbers, but there's no reason for any point in the fiber to be defined over the rational number. But these remarkable properties of torsion points on curves with complex multiplication mean that for certain cases, you can actually get points on the curve x0 of n defined over the same field. And these points are integral, too. They have a remarkable property that, just like the J invariant is an algebraic integer, these points have no intersection with the cusps when you reduce them modulo any prime p. And these points are now called Heegner points, because a German mathematician of the 20th century, Kurt Heegner, used these ideas to show that there were really only 9 imaginary quadratic fields that had class number 1. And I'm going to end with an attempt to show you, using these Heegner points, how his argument went. Here's a picture of Heegner sitting in his mother's garden in Berlin in the 1930s. He was a radio engineer. He was not a professional mathematician. And in particular, his work, well, it wasn't initially accepted by the mathematical community because it was written in a sort of a 19th century lingo. He supported himself on the patents he made from radio engineering, but unfortunately, those patents became worthless at the end of World War II, and he ended his life in great poverty. He didn't support in any way the Nazi regime, and his brother, in fact, was seriously penalized by the Nazis. He sort of removed himself from it all. So here's a sketch of Heegner's argument. First of all, recall that we know that there are 9 imaginary quadratic fields of class number 1. So that's a given. We want to show that there are no more. So if you have an imaginary quadratic field and you have an inert prime, the curves with complex multiplication give integral points on a certain modular curve, not x0 of p, but a related modular curve, which is determined by a subgroup of SL2Z reducing to the normalizer of a non-split Cartan subgroup in SL2Z mod p. So you get a point on this curve, and it's first of all an integer point, and it doesn't reduce to any of the cusps. And so if you can enumerate the integral points on this curve and show that there are no more than the ones given by the known fields of class number 1, then there are no more fields of class number 1. So if you can write down equations for this curve and find the integral points on it, then you've solved the class number 1 problem. So it turns out that when you take p equal 11, this modular curve has genus 1. It's an elliptic curve, but it has an infinite number of rational points. However, only 7 of those points turn out to be integral with respect to the cusps. And some of them correspond to the fundamental discriminants, and the remaining 3 correspond to what are called non-fundamental discriminants. But in particular, there are no more fundamental discriminants of class number 1. But Heegner himself did not refer to modular curves at all in his paper. He just used the modular functions that he found in books by Weber and Fricke, and from these modular functions, he found Diophantine equations, and he solved them in integers, and he showed there were only 7 solutions in this case. Now, unfortunately, as I say, he was not a professional mathematician, and no one fully understood, or, one should say, believed his paper when it was first published in 1952, and so the class number 1 problem was considered an outstanding problem. As Brian Birch remarked, unhappily, in 1952, there was no one left who was sufficiently expert in the books he was using, Weber's algebra, to appreciate Heegner's argument. Fortunately, several years afterwards, Baker and Stark solved the class number problem using slightly different methods, and then people like Birch and Carl Ludwig Siegel went back and looked at Heegner's argument and found out that it was fine. So I think he should really get credit for it. He was really working outside the mainstream. It was a miracle that he even got the paper published in Mathematische Zeitschrift. Now, this situation would change dramatically in the next 50 years. There'd be a resurgence of interest in complex multiplication, a resurgence of interest in the modular curves, in modular forms, and in particular in L functions of elliptic curves. And that's what I'm going to talk about in the next lecture. I'm going to do the next 50 years, which is a real explosion of interest. So we'll study how to define the L function of an elliptic curve over the rational numbers, what the Birch-Swinnerton-Dyer conjecture says about the L function and how it's related to the rational points on the curve. We'll study how that L function is related to modular forms. And then we'll see how the theory of complex multiplication, when combined with these modular forms, gives us a way to attack the Birch-Swinnerton-Dyer conjecture and produce rational points on elliptic curves over the rational numbers. So I know this is a lot of material. I appreciate that it's difficult to give this to a general audience. I hope you've enjoyed this talk. Thank you for listening. I hope you'll come back for 2 more, or at least 1 more. And so the next lecture will be 1952 to 2002, and the third lecture will be the developments that have occurred in this century. Thanks very much. Since there's a little time, I'm happy to take questions and try to clarify. Professor Rivet. How do you know that 11 is inert? Well, it turns out that once the discriminant is large enough, all the small primes have to be inert if it's class number 1. So that was a hidden part of the argument that I didn't give. Other questions? Henri. Yes, you can. So, the question, so I said that I used the curve, for p equal 11, which has genus 1. You can use the curve for p equals 7 or even p equal 5, which have genus 0. You have to make sure that there are enough cusps. So for p equals 7, there are enough cusps so that, there are only finitely many integral points. So you need 3 cusps at least. If you get too small a prime, then there are an infinite number of integral points and you can't do anything with it. 11 is attractive because the elliptic curve is one of the first elliptic curves of rank 1. And just, I mean, the existence of many integral points suggests that there'll be an infinite number of rational points. You won't get away for free. Other questions? Okay, well, there's a question here. One more.
Why was it that there were 9 fields with class number 1 imaginary but only 7 points?
Because the prime 11 is not inert in all of the imaginary quadratic fields of class number 1. You only get the primes, the fields of class number 1 where the prime 11 is inert, gives integral points on those curves. And if the prime splits, like for square root of minus 7 or something like that, then it doesn't give a point on that curve. But as I said to Ken, once the discriminant is large enough, in particular larger than minus 163, the prime 11 is forced to be inert in class number 1. Okay, see you all tomorrow.